You can see my screen.
Yes.
Okay, very good. So I'll just introduce myself, and then there'll be an opportunity to introduce all of you here. I'm Bhairav Mehta. I'm a principal data science manager at Microsoft. I've been working there for the last 9 months. I work in their operating system and security areas of core operating system. Mainly around data science and machine learning. Before that, I spent 10 years at Apple in their operating system diagnostics for Mac OS and iOS. And last part of my career at Apple, I was designing charging algorithms and analyzing power-based telemetry from the iOS devices and Mac OS devices. So that is my experience. Before that, I worked at Qualcomm, where I was a yield modeling engineer in their fab in Taiwan, TSMC, where we built first and second generation of Snapdragon processor that are part of most of the smartphones today. And I also worked in optics and the microelectromechanical systems, again, looking at computational physics and statistics. Before that, I spent a significant amount of time, around 3.5, 4 years at Philips, doing their optics and the light engine for the LCD screens and projection televisions, mainly computational physics. And then before that, I worked in auto industry in cooling systems, drive system, timing systems, fluid systems, modeling computational mechanics, and doing industrial statistics in their factories in companies like BorgWarner and Visteon. So that is my professional background. Before that, in India, I worked in nuclear power. Before I came to United States, I spent a few years in nuclear power plant fabrication. I'm an academician. I never leave school. I'm learning something and I'm sharing my knowledge with the students. So my latest degree I got from Georgia Tech in computer science that I received earlier this year. Before that, I have MBAs from Cornell University and Queen's University in Canada, and degrees in statistics and system engineering from mainly New England universities. I'm here to teach you computer vision today, and we are going to focus on computer vision with deep learning and a few other topics in computer vision. Computer vision has been around for a while. I taught a course at CSTU around 2 years back, more than 2 years back, to very high energy students like you all over 8-9 weeks. And we spent a long time teaching computer vision. But computer vision has come a long way since then. Right now, we are looking at computer vision with respect to deep learning with transformers and the segmentation models like you only look once or RCNNs. We are also looking at advanced libraries in Pytorch and in TensorFlow to do image captioning. That is also a big deal these days. And with OpenAI transformers, we are able to do a lot more with the images, and the emerging field of reinforcement learning used for self-driving cars and motion detection and obstacle avoidance, right? With reinforcement learning and generative adversarial networks, we call it GAN, creating hallucinating graphics and experiences out there, right? So those are advanced computer vision applications that can be used for augmented reality and virtual reality, and so on, right? And there's a whole new field of adversarial attacks on machine vision systems And we'll talk about it towards the end of the course, where we are looking at adversarial attacks on AI models, mainly computer vision models, so to change the output. So basically, we'll start with the basics of neural networks. For that, I'll need to know more about the students. So if there's time, we can introduce each student. But if there's no time, we can keep going. Maybe we can do the introduction later on in the class. So this is an introductory class for 2 hours. We'll go until 3:30 today, and we'll continue our class with more details around that. So what has happened in last few years? So you see, this is 2017 data. If I build a 2020, all the market caps of the 5 big digital companies, Apple, Alphabet, Microsoft, Amazon, and Facebook, has almost now it's almost 3x, or if not 2.5x, 2.5x of what it was 2017. So all these digital companies are becoming much more powerful than they were even 3 years back. All of these companies, like Apple's valuation is $2 trillion. Microsoft is 1.7 trillion. Alphabet is not too far, and Amazon is already more than a trillion, 1.3 or 1.4 trillion. These are market caps of these companies, and the amount of information and data they control is unprecedented, right? And then they are, and the second biggest is the government, and the third is the banks, the financial institutions. They own a lot of data about us and about our activities and all of that, right? So they become very, very powerful. So, and you see, just 50 years or 40, 45, 50 years back, this was dominated by telecom companies and natural resource companies, okay? So this has happened over the last few years. We call it as the Unicorn Club. These are not just companies in the United States. There are companies in China, Korea, India, Japan, and other places. So you see that how the number of startups have grown over time. And we are seeing a huge influx of revenue and finances, funding into these startups. And all of this is possible due to development in machine vision, in deep learning algorithms, in machine learning algorithms, artificial intelligence, cloud computing, telecom, 4G and 5G. That has given rise to this acceleration in startup ecosystem, and that's where the innovation is happening. So we are in the crossroad of 6 technologies, right? We have cloud computing, we have artificial intelligence, Internet of Things, data analytics, and fog or edge computing, and all around blockchain, right? So all this is very important, and for us to understand. Here we are going to focus on AI, but other areas are equally important, okay? So if you look at the hype cycle today, the deep neural networks and deep learning is at the high peak of expectation right now, okay? And if you see other technologies that are augmenting this technology, the hardware ecosystem has grown too, right? So you can look at the market capitalization of NVIDIA and AMD. They have done tremendous amount of work in advancing the field of computer vision in last few years by developing latest technology in the GPUs to process pixels and information at a greater speed, and parallelizing all these operations. And then comes the tensor processing unit, the TPUs by Google, and the Apple's M1 chip, the M1 chip at Apple, that really accelerated this whole machine vision and machine learning AI field by adding the CPU and memory in the same chip, right? So it added the M1 chip and the NVIDIA and FPGA revolution of Altera, and AMD is really, and Xilinx and others. And now that you put this in the cloud, you are able to even accelerate it more. So the tribes of machine learning, right? There are different tribes of machine learning. You have symbolists, right? These are symbolists are dealing with rules or heuristics, right? So this is how it used to be many years back, or even using decision trees. These are very primitive machine learning methods. They have been around for a long time, right? Since World War I, World War II timeframe, this was developed around that time. We call it symbolist. The applied statistics and the theory of statistics, theory of probability, right, from those days, right, with Dr. R.A. Fisher and Mahanolobis and a few other statisticians. They worked on, supervised and unsupervised algorithms where we send data and we send the labels, and it gives you output back on the other end. The Bayesians, based on Bayes' theorem, it's a purely probabilistic inference based on likelihood of occurrence, and they have been that is a very powerful technique based on probability, and it has demonstrated very good results over time, right? Then there are connectionists. Connectionists are what we're going to learn in this class is neural networks, recognize and generalize patterns dynamically with matrices or probabilistic weighted neurons. So these are connectionists, the cell body and synapse, and we are trying to emulate human senses like our eyes, our ears, our nose, our tongue, our skin. All of this can be emulated with these type of connectionist paradigm. So our brain is full of neurons. There are last number that I had was human body has 85 billion neurons, 100 trillion synapses. Okay, so you imagine how many neurons our body has, and as the baby grows from being newborn to 18-year-old, the neurons are firing and more neurons are produced. And that's when it gives them ability to learn multiple languages when they are young, and also have ability to do many things that they cannot do after they turn 18 and older. Connectionists. So basically, our brain has several centers. It has visual cortex, it has audio cortex, it has prefrontal cortex, it has smell, taste. All of these have different centers on our brain. Different parts of our brain has different centers. And these centers process information that we see from our senses. So our eyes see and send the signal to that audiovisual cortex, and it processes information, sends it to the prefrontal cortex, because that gives us our limbs and legs to walk, and we can balance while we walk. And then all of those from prefrontal cortex, the signal goes to, as I'm showing here, you see here on the right-hand side, you see it from your eyes, it goes to the visual form edges, corners, then intermediate visual forms and features, then high-level objects, then it goes to categorical judgment, then it goes to motor command, and then it goes to the spinal cord, right? And then our spinal cord makes our hands and legs move, right? So this is how the neural networks are designed, okay? That's why we call it cell, body, and synapse. So we are trying to emulate human senses, human brain. And that's how we create layers. And this field used to be popular in neuroscience. That's why if you see Dr. Hinton is a neuroscientist. He works at Google now, and he's a Turing Award winner. He was a neuroscientist. And they used to work with fruit flies. So that's why we have this fruit fly neuron. You see here, right hand side here, the image here is a fruit fly neuron that is collected from library in Spain, Madrid, Spain. You see a fruit fly neuron here, the image. It's in 1999, Santiago Ramon collected this neuron from a fruit fly. And then, so if you look at any Dr. Hinton's introductory video, he talks about fruit flies because it is like their bread and butter for neuroscientists. This is where they do most of their experiments using the fruit fly neuron. So they create this computer vision architecture where they are looking at different layers of information. First is you have broad spectrum, and then slowly you are reducing the form factor and the number of neurons, and you're getting to a point where you are able to get the score that can be converted to probability of detecting what that object is based on your training. So you can put any image into this network and it will tell you what that object is. It can segment multiple objects in an image. It can caption the image. It can do a lot of these things. Evolutionaries generate variations and then assess the fitness of each for a given purpose, right? That's the evolutionaries. Right, genetic algorithms, genetic programs generate variations and then assess the fitness of each. This is a genetic algorithm like reinforcement learning. And then you have analogizers where you optimize the function in light of constraints, right? Going as high as you can while staying on the road, right? So this is the support vectors. So these are all different types of tribes of machine learning algorithms. We are going to focus on the connectionist at this point, okay? That is important. So this is how any machine learning method works, right? This is how it works. Um, you have your raw data. Raw data can be images, audio files, video files, right? That's raw data, right? You have to put in massive amount of raw data into the machine learning model. You have to put the labels in there too, and you extract features from it, right? Feature extraction is very, very important. That's why I say for the machine learning engineers, feature learning or feature engineers are highest paid because they have the information, right? They have the features and information extracted from the model, okay? That's a feature extraction. So feature extraction is important. That's how you're going to get there. So why is deep learning and AI so important? Okay, why deep learning and AI is so important for computer vision? Because computer vision, our visions are very, very complex. Our visions are very complex. We can, even when we are 1 year or 2 year old, our parents tell us that, okay, this is the chair, this is the table, this is called a computer, this is called a fan, and we watch it. And next time when we see similar object, we're gonna say, hey, this is a chair, this is a table, this is a fan. So we are developing that cognitive ability. How can you make the computer learn that, right? How can you make the computer learn that this is a chair, this is a table, this is a computer, this is a fan, this is a speaker, right? So that's where the key ingredient is, right? That's where the key identity, right, can be identified using not your vision, but the computer vision. So neural networks are good at doing feature extraction so that humans don't have to do it. Because think about it, like from a cat and a dog, how can you decipher if it's a cat or a dog? If you see it, you can, as a human, we can say this is a cat or a dog. But how can you teach a computer to decipher the cat and a dog? You have to take every smallest component of the image, like 3 by 3 pixel of the image, and then train it, right? That this is a dog, and that those weights will be combined and stored in the model. The next time a dog image is shown, if it has similar eyes, similar ears, similar hairs, it will say that this is a dog, okay? So that's where feature extraction come in, and deep learning and computer vision type of application for deep learning, it helps you extract features without you specifying the rules. The way it is designed, it will automatically do it for you, okay? So that is something you want to keep in your mind, that why neural networks are so important today, because it can do the feature engineering very well, okay? It can do feature engineering very well. So now that being said, you do the feature extraction, then you train the model, So when you train the model, you are storing the weights, right? And when you store the weights, you have the model. After you store the weights, you can put it in a model, and then you can evaluate the model. Okay, once you put the weights in the model, you can evaluate the model, and that model can go back to the train the model, right? And then you go in that spin. So you have new data, you have feature extraction, you have prediction, and you have labels. Okay, so all of this process that you are looking at here is for the new data. So once you have the model, you have the key to the safe. So now you can take that key and predict as much as you can. But that prediction is as good as your model. If your model is not good, if you did not train the model with a vast amount of data, the prediction is going to be incorrect or biased or unfair, right? Or non-trustworthy, right? So if you're spending all that time building a machine learning model, you will have to be able to predict. Okay, you'll have to be able to predict. Okay, so that's the new data. You do feature extraction, you predict, and then you get the labels. Okay, so that's the machine learning modeling process, and it's a very important for you to consider that. Okay, so this is the area of probability. So what the job is, your job is to classify red and blue dots. Okay, these red and blue dots can be cats and dogs. These red and blue can be fraud and not fraud. This red and blue can be spam or not spam. This can be buy or not buy. It can be any of that, right? So your job is to classify these two dots. How are you going to do it? You can put it through the classifier, right? Neural network classifier, or you can put traditional classifier, and it will create this problem space. The red and orange waves that you see in this images, that shows the nature of the method, right? So if you see very jagged lines, then it's a brute force method, like k nearest neighbor, very computer intensive near brute force method. If you see a rectangular surface with a lot of corners, then that is a decision based method, or for that matter, a rule based method. And if you see fringes of lines, right, those fringes of lines are probabilistic. If you see a circle or a curve, it's a probabilistic method. Okay, so I just want to show you different type of machine learning, how it works. So a neuron can be have a nucleus, it has a cell body, it has dendrites, it has impulses carried towards cell body, branches of axon, impulses carried away from the cell body, axon terminals. So this is our neuron that's in our brain. All of our brains have 86 billion neurons and 100 trillion synapses. Now, what is a synapse? Synapse is when the information passes through the neuron, and neuron thinks, and then if it has a preconceived notion or a weight of that type of particular object, it's gonna snap. It will snap, and it will send that signal to the next neuron that, hey, this is what I figured out. Now you take it from here, right? So that's called synapse. 100 trillion synapses. Okay. And what you have here is the inputs, x0, x1, x2. This can be a set of pixels, so it can be voice packets, it can be information packets, it can be data rows, it can be anything, right? That's the x0, x1, x2. And w0, w1, w2 is the slope of the line or weight of the line. So when you fit a line to a surface, it gives you a slope. That's a w0. And in reality, there's nothing goes to the origin, right? Nothing is ideal in this world. Everything is real. So when you have reality, then you have bias. So you are looking at bias here. That's called that's called B. That's Wx plus B. So we do this operation called mat-mul. Mat-mul means summation and multiply. Okay, that's the function of summation of Wi xi plus B where function is an activation function. The activation function is like, it's like a bucket under the water, So you fill out a water, you start the tap, and then the water will fill in the bucket. And at some point, it's going to tip out. It's going to start flowing out, right? We call it threshold. That's a threshold of that water flow, or that container. It cannot store more water beyond that capacity. Similarly, you have in neural networks, it's like you're filling up the water, and when it reaches the threshold, it will hit that. Okay, so this is okay. Yes. So there's a thing called curse of highlight, right, or curse of dimensionality, right? So thank you, Professor Quinn. So you have curse of dimensionality. So what happens is, in some processes, you have too much information, like a self-driving car, right? You're tracking, like you have a sensor fusion. You have 18, 20, 50 sensors, many cameras on the car, trying to see what's in the front of the car. So it's looking at all of these sensors, and all of these sensors, the information is going through. So what Dr. Quinn just suggested is a curse of dimensionality. So you have so many sensors coming in with information. It's very difficult to model all of them using traditional methods. You'll have to have something called neural networks to support the curse of dimensionality that I'm trying to explain here. And we'll do some examples, you will know better. And then here you have the activation function, where you have the threshold, and when the signals hit a threshold, it's going to activate. Okay, so that's where you have function, activation function. It can be a rectified linear unit. It can be a 10H or a sigmoid function. So the sigmoid is negative. 0 to 1, right? Like a logistic function. You have a sigmoid gate or activation function. Then you have a 10H is -1 to +1, right? So -1 to +1 is a 10H, right? And then you have ReLU. ReLU is a 0 to infinity. So it hits the threshold and goes to infinity. We'll go through each of these functions in detail in a moment. So this is what we have here. And what we are looking at here is a neuron, a physical neuron modeled as physical neuron model in terms of numbers and mathematics equations. Okay, so it's very important for you to consider that. Okay, so this is the brief history of AI or even computer vision until 2008 or 9. So you have 1958 is Rosenblatt perceptron. He discovered the perceptron. He gave the name multi-layer perceptron at Cornell University. Then 1974 was the invention of backpropagation, where they said, okay, we can do backpropagation and continue to improve and refine the signals as they pass through the neurons. And then you have the Jan LeCun at New York University. In 1998, he came up with the word called convolution network, and that really changed the world of computer vision. And Dr. Wapnick at Columbia University developed something called support vector machines. And then Dr. Hinton from University of Toronto built restricted Boltzmann machines, right? And he was instrumental in publishing two key papers that explained how to train a machine vision based information through neural networks and get very high accuracy. So he explained that using the restricted Boltzmann machine. And then 2007 was stacked autoencoders. And then now we are talking about transformers. It's all because of Dr. Bengio and the Microsoft He helped in Microsoft with the acquisition of one of the Maluba, is one of the audio uh, training engine. He built along with others. He developed the long short-term memory, recurrent neural networks, and then 2012 Google Brain Project and other aspects of Google's projects. It developed that led to beating AlphaGo a few years back. And then 2014, Dr. Ian Goodfellow, he developed generative adversarial networks. So Dr. Goodfellow works at Apple now, and he's from Stanford, and he worked on generative adversarial networks. So this is a history of deep learning and computer vision, basically. So what is the impact of computer vision today compared to a few years back, right? So if you look at from 2010 to today, what is on the x-axis is all the different networks built by these companies, okay? These companies have built networks, and these networks are essentially a complex architecture of neuron arrangement, right? Number of neurons, then you have number of layers, then you have regularization. We will go through all these topics in detail in this class, and all the students will be able to architect their own computer vision model, okay? And they'll be able to understand all the different models that were built in the past. So basically, this what is showing is error rate in image classification. So let's say a 90-year-old man, or maybe a 1-year-old baby, it's very difficult for them to identify objects so easily because they don't have the information. So they will come and show you, okay, what is this called? And you have to explain that this is called, this is the red color, this is the green color, this is a car, this is a bus, right? So you have to tell them, and then over time, when they repeat so many times, you're able to remember it as a child. So what was going on in 2010 was 30% of time you identified as incorrect. So in 2010, it was impossible to have a computer vision system that can be used for self-driving car or for detecting objects, right? A robot walking around, right? But as the time progressed in 2012, 2013, that error rate went down to 10 to 12%. And then all the way down to less than 5%. And now we are looking at almost zero error, 0.01% error in computer vision system that is put in Tesla, that is put in all the self-driving cars, right? And other vision systems, right? The error rate is almost zero. So our human performance zone is 5 to 10% error. So when you look at an X-ray, and you're a pathologist, or if you are a radiologist, you look at an X-ray, and by looking at an X-ray or an MRI scan, you should be, as an experienced pathologist, you should be able to say that this is a tumor, malignant or not, right? Because that's what you're trained for. But still, 5% of times there's misdiagnosis, right? I had my personal experience. I sent my pathology slides for some outgrowth I had in my throat, and I sent it out to the pathologist, and they said, hey, you have the worst form of cancer you can be. And then I sent a few more times to different labs, and eventually there was nothing, right? So there's a 5% chance that even the experienced pathologist is going to make error, right? So you're going to see that this computer vision is even better than that now. Okay, so that's why we are teaching this course, and we'll see the power of computer vision. Okay, so that is the and all these models that you see on the bottom from 2020 to 2017, it was like competition between Google and Microsoft. So one year Google created the model, the second year Microsoft beat it, then the following year Google beat it, and then Microsoft beat it again. So they kept on going until 2018, until the error rate became almost zero. Okay, so that is the computer vision. Okay, so if you see a neural network, right, you start with the car or person, animal. Sorry, you start with the visible layers, right? You input pixels, and then first hidden layer gets the edges. So now you see that image of a lady. Right now, let's assume that it's just looking at the small pixels that are taken from the one of the corners of that image, and then it goes through each of these layers, and in the end it identifies it to be a car, person, or animal. So it starts with the edges, then goes to the corners and contours, and then goes to object parts, and then goes to the object identity. Okay, so you are able to go from bottom to top and be able to identify an object, right, by going from edges to the corners to the bigger objects, and then the full object. Okay. I think we'll have to put students on mute. Yeah, there's some disturbance. Okay, so you can see here where our brain centers are, and you are trying to replicate that with these layers. Okay, so so basically, this is what we are trying to build. Okay, so this is what we are trying to build, right? You have the neural network, and you are creating, you're building, you can add as many layers you want, as many neurons you want, and you're able to create a complex neural network, right? And able to run it through, right? So you have put in all these configuration of learning rate, activation, regularization rate, classification. You're able to put in all these details and be able to say in detail what it is all about, right? So you can put in, you can start this network, and then you see over time it's able to detect and classify. You see the orange is in orange, blue is in blue, and you see what happened. The first is all edges, then little contours, then corners, then real objects, then the layers of the object, and then the last one is the final output. And you see it started with 100% error and went down to 0 later on. Okay, so this is a much more complicated network, and we'll see how long it takes to fit this type of orange red, orange blue alternating surface. Okay, so you'll see that here. So it will take some time, and you'll be able to get to that, right? Then the other ones are, so this is the simulation that we can look at, right? So we can say number 3, this is how the network is going to comprehend it, right? Number 2, it says number 2 here, right? It can be an image, and it will do it for the image also, right? So let's say I do a basic network here. It's a Google's inception layer, and it will initialize a model, and we'll be able to run the data through it, right? So this is initializing the model and going from there. here you can see I'm going to select an image of a dog. And you see Newfoundland dog. Or I can select airplane. And you found an airplane. So basically, you can select any object. It will pass the signal through the complex network here. And it will give you the answer based on the pre-trained model. These are all pre-trained models that I was showing you. These are all pre-trained models I was showing you, all of these, okay? So this is how we're gonna learn how to build this network and program it in Python, okay? That is the goal of this class. You're gonna learn different techniques, different models, different ways of architecting the network. So for example here, this is the introductory class. I can jump around here. And I'll show you this from Stanford University. You can see how exactly the computer vision networks work. So this is the airplane, right? And it's going through different layers. You see how the images are getting transformed and the form factor reduced. And in the end, you're going to see that it's an airplane or not, right? So this is the this is another airplane, right? And it's showing you the information. And over time, if you're gonna improve, the accuracy is gonna improve, okay? So this is the handwritten numbers images, right? So it's handwritten numbers and number 5, what number it is, right? It's still not getting the right answer, but over time, it will learn and train itself, you see. So it's going to improve over time. And we'll program this type of networks in this class, okay? So you have all of these networks, and then this is how the composition is, okay? So that being said, you see this is still not happening. I came back to this just to see if it's able to train or not. It ran 200 or so epochs, it's still not working. So what we're going to do is we're going to increase the number of neurons and see if it works. Okay, so we'll see if it improves. Okay, I don't know if it will, but from my experience, it takes time, but it will improve. Okay, we'll come back to this later on. So basically, you can look at something like this, right? So this one is another set of network where you can simulate a network using like it's a 3D depiction of the model, and this will give us a good idea on how exactly it works. And you are able to show very clearly how the architecture works. Oh, you don't see? You don't see my screen?
We can see your screen.
Okay.
Downloading.
I don't see the screen. I'm sorry. Sorry for my interruption. I don't see the screen.
Okay, then you may have to disconnect and connect again.
Okay, thank
you. Yeah, so this one is showing the AlexNet model. This is a beagle dog here, and you can see how the whole network is how it breaks down the image into so many different pieces, you see. And then it goes to the next one. Each layer in itself is an architecture. Okay, it's each layer has its own way of capturing information from the image, and all of this data goes in and creates a weight file. And next time a similar image shows up, it will go through this filter and it will say that, hey, you know, this matches. This seems like similar to what the previous training was done, and it will classify that information. Okay, so you see that number of images are going becoming smaller and smaller, and you see how the fringes are. So you can trace each image into several where it is coming from, right? What part of image is coming from. So you can see how it's working, how the networks are created, right? So this is called convolutional neural network. Okay, so you see this is the largest one, and then you have a flattened layer, right? Which is a flattened layer is usually fully flattened. They come and flatten the whole thing just for the sake of classifying, right? The probability. So you see now we have ones and zeros on the other end here. Last layer here is, it takes all these pixels. It's like you have a noodle. You are stretching the noodle, right? So you have the whole, all these images. You are stretching it to a point where it becomes flat, and then each item can be classified as ones and zeros. Okay, so I just wanted to show you what exactly the science is all about in computer vision, and why it's so powerful compared to any other previous computer vision science was there before, right? This kind of replaced all of it. Okay, so so these are some of the engines. I will share the link with you. And still this is not working, you see. Maybe it will get there in a few minutes. There we go. It's catching it now. You see, it's kind of, you see that tipping point here. It came down. The training is doing better, and then I think it paved the way. And in a few seconds, you see the orange line is coming up. So over time, you're going to see that the training, the weights will be. See, now it started jittering. It started jittering, and now it's going to twist. Okay, so this is a purely training process. You see how the neurons are modifying. Okay, so what you're going to do, what we are going to do now is basically take this understanding that we had until now. We are going to turn it into a into a programming problem. Okay, right? Until now, we are just looking at and feeling different things. But how do we do it in programming, right? How do we do it in programming? Like, how do you do it in TensorFlow? How do you do it in Keras? How do you implement it in different programming languages? Okay, so this is the way to go here. Okay, so so I went through this. I'm not going to spend time on these items here, just news items. So what is an intelligent system, right? What the intelligent system needs to possess? The intelligent system needs to possess, you need the data sources, definitely user data, enterprise data, financial data. It needs to go into to store complex information, knowledge representation. Then it gets into automatic reasoning, natural language processing, and then machine learning, augmenting it. And we are building a capability to communicate information with humans, answer queries, infer new facts, and store complex information. Okay, so what does the AI implies? It's a machine that can reasoning, knowledge, planning, communication, perception. It's ability to solve problems through optical deduction, logical deductions, the ability to represent knowledge about the world, the ability to set and achieve goals, the ability to understand written and spoken languages, the ability to deduce things about the world from visual images, sounds, and other sensory inputs. That's artificial intelligence. There are 12 types of problems that AI can solve. You can become a domain expert, problem which involves reasoning based on complex body of knowledge. Domain extension is a problem which involves extending a complex body of knowledge. Complex planner is tasks which involve planning. Better communicator, tasks which involve improving existing communication. New perception is tasks which involve perception. Enterprise AI, AI means re-engineering the corporation. Enterprise AI adding unstructured data and cognitive capabilities to ERP and data warehousing. Problems which impact domains due to second-order consequences of AI. Problems in near future that could benefit from improved algorithms. Evolution of expert systems. Super long sequence pattern recognition, and extending sentiment analysis using AI. Right? These are all different types of AI problems you can solve. And what you have is architecture, right, of different type of AI models, right? We went through this, right? So this is a neuron model I was showing you from Santiago Ramon. The second step was Frank Rosenblatt, backpropagation, recurrent neural network. And I already showed you this slide. We are getting into the architecture. So why is it called deep learning, right? It's called deep learning because you like world is complex and reality is complex. So you can't put it in one neuron. You have to put it in a lot of neurons, thousands. I showed you that simple circuit that we were trying to fit that alternating. See, now it's still doing it, right? It's getting there though, right? It's trying. Okay, it will work in a few seconds. Okay, so basically this is deep network, right? Deep, you go deeper in the network, more neurons, more layers. That's why it's called deep learning. Okay. 2006 breakthrough is more data, faster hardware, GPUs, multi-core CPUs, working ideas on how to train deep architectures, and you have the breakthrough in 2006 where they published this paper. The two papers were published in 2006-7. One was the fast learning algorithm for deep belief networks and greedy layer-wise training of deep networks. So these two papers explain what we are going to implement in this class. So it started in 2006. Before that, there was no computer vision using deep learning. It was very, very inaccurate. Okay. So big data is definitely a big deal, right? Your big data algorithms and storage became cheaper, and there were breakthroughs in storage. Faster hardware. You have more advanced CPUs and GPUs, and then you have the working ideas. Algorithms were developed, and all of this kind of came together. And this is what happened in 2012. So 2012, there was one paper published that showed promise of deep learning, and it was below 15% error rate. And then at this point, it just switched. Next year, everybody started doing that. Okay, you see, so like it moved from traditional computer vision to deep learning in 1 year. That was a breakthrough, and nobody went back to original because the error rates were so low at this point. Okay, and this is the accuracy versus years, and you have your different. So from 2012 onwards, you see the accuracy of detecting all these objects have gone significantly, and you have plants, person, chair, cat, car, airplane, and all classes. Cars is the top, then cat is the best accuracy is the cat, and then comes aeroplane. And because if you take all the images on Google Images and YouTube, you will see most images are of cats, followed by airplanes. Okay, and yeah, so they and then cars. So most videos and images are of cars or cats or airplanes. That's why they have more data to train and higher accuracy, followed by person, and average is more than 65%. So then, you have this type of architecture. So Google said, okay, Microsoft wants to go deep, I can go wider. Okay, that's how they were able to develop that. Okay, very good. Thank you, Angel. Um, so you can go. So Google said we're going to go wide and instead of deep, and we're going to develop these networks. Okay, so this is what they did. And then you have the Google Lenet, and then deep image is Microsoft, Google, deep image. So you see the error rate continue to go down, and now we are at less than 1% error rate. Error rate means that how many times it misclassifies objects. This is same thing happened with the audio processing, and same nature. You know, the error rate went down, and this is a log scale. And all the speech recognition models also follow deep learning now. You see from 2010 onwards, everything is deep learning. Okay. So as I said earlier, it's all these three guys did all the work, and then they're hired by the large corporations. Dr. LeCun is responsible for Pytorch, and the torch is from New York University Pytorch. Okay. And then you have TensorFlow and Keras from Google by Francois Collette and Dr. Hinton. And with the Dr. Bengio is stacked autoencoders. And then, then these are all history of these guys. So how do you build the neural network? Okay, so let's talk about the architecture. Okay, so we cannot gonna worry about these slides here. We're gonna go to the architecture. Okay. So there are 24 adjustments you can make in neural network. Okay, so this is what we will learn in this class, is the 24 adjustments. So what are those 24 adjustments? The 24 adjustments are architecture, variable type, variable scaling, cost function, neural network type, number of layers, number of hidden layers, number of nodes, types of layers, types of weight initialization, type of activation function, dropout rate, threshold, type of optimizers. There's a hyperparameter tuning. So that's first is architecture, then hyperparameter tuning, type of optimizers, learning rate, regularization type, type of search for local minima, gradient descent, simulated, annealing, evolutionary, batch size, Nesterov momentum, decay rate, momentum, fixed or not, types of fitness measurements, mean squared error, accuracy, mean absolute error, cross entropy, precision, recall, epochs, and stop criteria. Okay, so these are all different adjustments we have to make, and we will learn by doing this stuff, right? We learn by doing this stuff in detail, right? We will learn every aspect of these names and where do they apply, how do we architect a computer vision network, how do we design the vision system, how do we deploy it on the cloud, and so on. There are several architectures that have come up over time. So the first one is symbolic or imperative, well, Theano. Then symbolic is Theano, Cafe, CNTK, TensorFlow, Keras, Cafe2, MX9, Chainer, Pytorch, Gluon. These are all different names of the platforms or frameworks that are out there to develop these deep learning models. And TensorFlow by far is the most popular, followed by Keras, and then Pytorch. Okay. And there are different levels of abstraction there, right? So there's web API, pre-trained models, train your own model, design your own architecture, right? All these are the methods. And then deep learning library Zoo, there are different libraries, as I said earlier, different type of deep learning models. And pros and cons for each of them are mentioned here on each of the models. Okay, so essentially, the application of computer vision is unlimited, right? Because wherever our vision can go, the computer vision can go and do a better job at it. Okay, so let's take a 5-minute break, and then we will come back and continue with more details around deep learning and computer vision. Okay, we'll show some demos, and we'll also answer any questions you may have. Let's take a 5-minute break.
Okay.
Used to differentiate, right, and identify objects clearly. Okay, so we are going to go through some examples now on how to program it using Pytorch and using TensorFlow. And we'll also go through the applications. Okay, so just bear with me for a minute. So what we are looking at here is the slides on how to detect a number 8, right? It's a computer vision based handwritten. It's a handwritten number 8. Okay, so this number 8 is a 28 by 28 pixels. So you can stretch the 28 by 28 pixels become 784 pixels, and each of these pixels you can apply a softmax classifier, and based on the pattern, it can be trained for detecting number 8. If you're given multiple, like let's say we have around 30 students in this class, and all of you can write number 8 in a piece of paper, and we can convert that number 8, handwritten number 8, into 28 by 28 pixel image, and we pass it through this neuron, this very, very simple model of neural network. It will take those patterns of ones and zeros or black and white, and it will store it in those neurons, and then store it as a weight, and then convert those weight, the scores into probability, and say, okay, this is number 8, okay, based on training that we have provided to this, right? And then you can have all these different numbers like 8, 4, 6, 6, 4, 3, and each of these have an array of ones and zeros or black and whites, and each of these can have weights because you'll fit the weight W00, W01, W02, W03, like that, 784 of these. Let's say you invert this, right? You take this matrix and flip it. There will be 784 weights, for one weight for each pixel, right? This column is for number 8, this column is for number 4, this column is number 6, and the last one is number 3. Okay, and then you have 784 lines, there are 784 pixels here, and 10 columns of 10 numbers here. And you're able to get y equal to mx plus c, or l equal to xw plus b, where b is the bias or intercept, weight is the slope, and x is the input. Okay, so this is important. So you're going to get each of these as an axis here, x, and then get the else. That's the output function. Okay, so that's your biases and variance, bias and weight. So this is your prediction of 110 softmax applied line by line, matrix multiply, weight, biases, and tensor shape. Okay, and then you can program it. So this is how the simple network works. You see you have accuracy, you have cross entropy loss, you have weights, so you have biases, you have training and test data, and as the numbers pass through, the accuracy goes from 0 to 100%. The loss goes from 100% to less than 15%. The weights grows, the variance grows in the weight, and the biases variance also grows. Okay, so this is the basic demo of how a neural network is trained as the number passes through. Okay, so you see 92% accuracy. I'm not going to go into code right now. And then you have softmax cross entropy. You go deep. So this is called a fully connected network. And you take the number 8, the 784 pixels, and you pass it through the neurons. You apply the sigmoid activation function, and you get some kind of response there. Okay, and this will store your probability of a given number. In this case, 8. 8 should have the highest probability. Each of these neurons have activation function with a sigmoid, right? A sigmoid shape. Okay. So here you're looking at accuracy, cross entropy, and you apply the ReLU function. ReLU is a rectified linear unit, which looks like this, and you pass it through the network, and that improved the and made it much faster. In 350 300 epochs, you are able to reach less than 20% loss. And then you have the noisy accuracy curves, right? Noise is not good, but you are going to see accuracy curve of the test and train. The test is much more noisier because a lot of trial and error going on, and that's the reason. So learning rate decay, you can apply learning rate decay, and that will improve it. Okay, so this is the fully connected layer being applied the training. Do you see something abnormal here? The training loss is going up. You see the red line going up. That is abnormal. That's called overfitting. So we are seeing overfitting because we have trained it. Our training data is not enough. We have not applied regularization to this particular network, and that's why you're seeing overfitting. Overfitting, what it means that the training loss, almost zero. You see, the training went all the way down to zero. But the testing goes up, means that the training, something was wrong with the training. There was not enough data. There was other issues with the training. Maybe the data was not versatile enough. You did not train long enough. You didn't run enough box iteration. Your network was too rudimentary. There may be 10 different reasons, but there is a way to avoid overfitting in neural networks called regularization. We call it dropout regularization. You can apply the learning rate decay, and that will improve it too. Okay, but then you have the overfitting issue. Okay, the overfitting.
Professor, I have a quick question.
Yes.
What exactly is the loss? What does that actually mean?
I'm sorry, can you say it again?
Like, is you're saying the loss was going up, and that's why this overfitting. What exactly is the loss?
Loss is basically every time when you train an algorithm, right? Train a model here. You are comparing with the original. Okay, so what is the response? What is the response? So let me explain it a little bit more. So there's a training and testing. So you take the data set of 100 points, okay, 100 images in this case. You divide it into 70-30, right? 70% you use for training, 30% you use for testing. So now when you are training, you are passing the images through the network that I showed you earlier. And at the other end of the network, your training is going to show, okay, this image is number 3, but in reality, it was number 8. Okay, so that means that there's a gap between 8 and 3. There is some training issue. You need to retrain it. So you need to refine the weights and make sure that you get number 8 on the other end. Otherwise, there's no point. You're wasting your time because you're getting an incorrect response for what you have put in. You put in number 8, but your training is so messed up that you're getting number 3 as an output at the other end of the network. So ideally, what you can do is you can either increase the amount of data you use for training, you train it longer with more refinement, more back propagation, and you want to make sure you get an 8. But until then, your loss is going to be high. Okay, your loss is basically, in a very layman term, is actual versus predicted. The predicted is incorrect, then it's not matching the actual.
Wait, so then what's the difference between this loss and the accuracy?
Yeah, so accuracy is input output, right? So you're getting your input and you're getting your output. So it's just a 1 minus usually. Yeah.
Okay. And so in the case of this overfitting, it's not so much that I think the loss is going up, as so much as it's a difference between the training loss and the test loss, right?
Exactly. No. So training and test are two separate data sets. You're not using the same data to test, right? They are two separate data sets. So when you do training, you are training the data to the model, right? So you're training the data to the model, and that's how you build the model, right? By training the data, training on the data, right? So you are putting the data in, and it's going to do the back propagation. You're going to run multiple epochs, and you're going to create a model. The model is going to give you some type of accuracy. But the test data might be a little different, or a little bit, it's not definitely, it's not training data, it's different data set. So what happens is when the test data goes into that model that you trained, it is giving wrong answers, right? So it's giving wrong answers. So the actual and predicted are not the same. And when that happens, your losses go up. Okay.
Okay. So then would there be a scenario where you would see sort of like the training loss also going up in a same as your test loss?
Yeah, training loss. If training loss goes up, then you will keep training, right, until it gets to 100, like 0, right? So, but in the test, you don't have that opportunity to retrain, right? At this point, the training model is fixed; it's already locked in, and you are testing the data, new data on that locked-in model, and that's how you see this trend, because it's a derivative.
Okay. Okay,
Right?
got it. So basically the loss is just the 1 minus of the accuracy.
Yeah, I mean, more or less. Yeah.
Okay.
Yeah, more or less. Yeah. But losses go up, and you are gonna see the problem there, right? Okay. So that's overfitting is not not good, right? So you don't want to overfit, otherwise, because testing is emulating how the model is gonna be used by business. Your business is gonna use the model, right? And if it's giving you inaccurate result, there's no point using the model, right? So you want to, that's where the dropout comes in. The dropout is you are kind of creating randomization in the inputs and in the time of training, and that will avoid the overfitting. Okay, you want to avoid overfitting by introducing dropout, where it systematically, in a random fashion, remove some neurons from your model training architecture, and that will introduce randomization, and that will avoid the overfitting of the model. Because if you keep on sending similar data on the same template of these neuron patterns, there is an opportunity that it will overfit. And that was the biggest problem before the 2006 papers, that these neural networks always used to overfit, and that's why it was not useful. But then when Dr. Hinton published his paper in 2006 about fast training of networks, that's when he introduced dropout regularization. And once we added dropout, the time to train reduced, and accuracy improved, and the losses went down, and the overfitting went down also. Okay, so that's the training and evaluation rate. And then next topic, next thing is it will fix that issue with the entropy. Okay, losses went down, the overfitting stopped, and you are going to see that here. Okay, so this was an introduction to, in general, how do you understand different aspects of neural network, how do you fit the neural network, and so on. Okay, so now let's look at some applications. Okay, we have 30 minutes left. So let's look at some applications now. Okay, this is an example of a data set that is out there. It's called style fashion mints data set. Okay, so these are modern fashion mints data set. So basically, this data set looks like this. This is a fashion mints data set, which looks like this here. These are all different clothes. And different women, men clothes, trousers, shirts, sandals, different type of sandals and shoes, and women clothes, bags, and women's shoes, men's shoes, and so on. So you have all of this data, right, in this combination, okay? And what we're gonna do is we're gonna build a neural network using Keras to detect all of, first train using these 9 categories, right? These are all 28 by 28 pixel images that I was showing you. These are all 28 by 28 pixels. And we are going to first train on these images, and then we are going to test and predict, okay? So first we download, we are using Google Colab. This is what we're gonna use for our training, right? And we're gonna use Keras and TensorFlow. So we are going to download and install TensorFlow, and then download the MINS data set, and then we visualize the data. So this is one of the images of the shirt. So the t-shirt, I think, long sleeve t-shirt, and then data normalization, and then we create the model. This is the architecture of the model, and compile the model, train the model, and then we will test the accuracy, then visualize the prediction, okay? So we'll start with the, and this is as simple as it can get. It's nothing complicated here. So we were able to do this. We installed TensorFlow. We were able to get, download this data set. And next thing we're gonna do is we're gonna visualize the data. So now this is the shirt that we looked at, right? We are pulling that. We are going to show the image of the shirt. And then we're going to normalize this data. And then we're going to print number of train and test, 60,000 training images and 10,000 testing images. We're going to break the training data into train and validation sets. Okay. And then we're going to do 55,000 train, 5,000 validation, and 10,000 test set. We're going to get this is the network we are building. It's a convolution 2D. And then you see the filter 64, kernel size 2, padding same, activation ReLU, input shape 28 by 28 by 1. It's a monochrome image. Then you have max pooling, pool size 2, dropout, and then another convolution network, and then max pooling, flatten, and then you have the network here. Okay, this is the architecture of the network. Similar to what I showed you in the TensorSpace.js. This is the first layer is usually convolution layer. Then we have the convolution, and then pooling layer. Then again convolution, another pooling, then convolution, 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 pooling, and then flatten. Okay. That's what we did here. We did convolution, pooling, dropout, convolution, pooling, dropout, flatten, dense, fully connected, dropout 3, dense 2. Okay, so we are doing regularization at 3 points. And then I showed it to you here. We ran this model here. And then the next one is, next we are going to do is look at this guy. And then we build a model, Adam accuracy, Adam optimizer. We go through the optimizer later on. And then we have categorical cross entropy because there are 9 categories of different clothes. We train the model here. There was some error here. I have to check maybe the version of the program is different, or I did not run all the cells. So let me just run all the cells. So it worked, okay? So maybe I missed a cell to run. So now it's training. You see it is training the model. It's gonna run 10 epochs. If I have a GPU here, I can go in here and change runtime and add a GPU here. If I want, here it's already added. That's why it's going so fast. But if this GPU is not added, it will not accelerate and not do it fast enough. And then we'll be sitting here forever. And many times it just times out and fails. Okay, but we have enabled the GPU, and this one is running a GPU. Okay. So we ran the whole network, and now we have the training model. Now we are going to load weights. So now this save the model as model weights batch.hgf5. This is how you save the model. In this, now we are going to load the model from the saved, and this it's saved here. You see, it's saved here, and then we're going to load the model, and then score the model using the test data, and we got 90% accuracy. Okay, so it shows that we didn't overfit here because we had so much dropout regularization. And now we're going to predict. Okay, we're going to predict on 15 different images that we are randomly pulling from the data. So now we pulled, and it is quite good. Coat, trouser, sandal, t-shirt, top, pullover, coat, shirt, sandal, dress, coat, right? So it did a good job. Okay, so this is an example of how it really works. Okay, so we'll learn this in the class. We'll learn much more complicated models like BGG16. We will learn inception. We will learn convolution networks based on Microsoft ResNet 50 and other models out there, transformer models. So this was a simple one, right? So now let's see if we can do a complex image segmentation. Okay, image segmentation. So we should be able to do like object, like image segmentation, right? Using Keras and on Google Colab. Then we look at the Pytorch also. Okay, just give me a moment. Just give me a moment. What we are trying to do is we have these images, and we want to segment them, right? So Carvana is a successful online used car startup, has been opportunity to build long-term trust in the consumer and streamline the online buying process. Interesting part of their segment innovation is the custom rotating photos. right? So we want to take the image of the, like, let's say you want to sell a car, you go to Carvana and you give your car to them. But each car is unique. Each car has its own dents and scratches and blemishes. Old, new cars, different type of lights, different features, accessories. Some people have the wing and hoods and different type of sidebars and different type of mirrors and glasses and stuff. So customer would want to see it. They would want to see how the car looks when it's up, down, all different directions, right? So what this particular project is doing is it's called Carvana project, where it takes a photo of a car sitting in a parking lot, and then this engine will segment the car and remove the background of the car. Okay, it will just take the car and remove the background of the car. You see, this is auto editing, this is manual editing, and it's close, right? So in this competition, you are challenged to develop an algorithm that automatically removes photo studio background. This will allow Carvana to superimpose cars on variety of backgrounds. You'll be able to analyze the data set of the photos and covering different vehicle in the wide variety of years, make, and models. So you are supposed to cut this out, okay? So what we are doing here is we're going to run all of these here. So we're going to install Kaggle, pull all the images from Kaggle. Then we're going to run the operation here. Yeah, there's some bugs in the code here, so we're gonna fix it. So basically, this is what this training is all about, because there's a plenty of code out there. You should be able to use it. Okay, so so we should be able to just run this. I wonder what is going on. There we go. Yeah, so I have to fix this. Basically, what this is doing is it's segmenting those images, and the code is here. You visualize information, and then you set up, then you build your own pipeline using TF. So let me find another example, and we'll show that. Okay, because the versions keep changing, there may be some issues with that.
Are those your collab notebooks, or are those the ones directly from GitHub?
Yeah, I mean, it's all over the place. I have my own also, but I'm using from GitHub.
Okay.
So this is the example of object detection. You're seeing the objects here, person, dog, horse. You're able to detect multiple objects on an image and be able to well, see the license plate of the car and able to read it. There are other examples of identifying objects out there, right? Using you only look once, RCNNs. There's a whole thing called FaceNet. So we learn all of this FaceNet and face detection, right? So there's a FaceNet that you can detect faces and then celebrity faces, or you can train on that and then check in that case, right? Different type of face nets. So face recognition system, right? And then you can look at it in a more this is how it works, right? You detect face-to-face recognition, and you're able to detect faces of celebrities. So in this case, you see these are the images of the celebrities, different images. That's 36 images of a celebrity, and you're going to train using that. And then next time that celebrity face shows up, you are able to you're able to see it very easily. Okay, so this is that that process here. So here, when you send an image of Jerry Seinfeld, it's able to detect the image of Jerry Seinfeld by 88% accuracy. Okay, so you train the network and the FaceNet itself, and you're able to detect. This is how you train the FaceNet, and then you're able to predict the face, right? So there are many algorithms to even like Microsoft Celeb 1 million data set, Keras FaceNet project, OpenFace Keras project, or OpenFace Pytorch. There's a lot of work done on face detection, and that is for one other aspect of it. You can segment information, you can detect faces. Then other area of work is in this area is called generative adversarial networks, where you are able to create experiences that are uncanny, right? So in this case, you are able to change the objects, and you see here, let me share my screen. So this is the generative adversarial networks, where you have a generator and discriminator, and you're able to detect objects based on just scribbles of pencil, and then even more attempts later, you're able to detect it's the cat. So you see, you're able to generate content as the letters are being written or morphed into different forms. So this is an example of that, how you can create that type of experience that I just showing you, of generating images based on various different forms. Okay, so let's see here. If you're able to show it too many sessions. Okay. So here you're able to show different type of models here and how it can be trained. This may take a little longer to train and test in itself, but it's able to create this morph type of experience where you know, there's a website called This Person Doesn't Exist. So this person does not exist.com, and these are all the images of people that's created using this generative adversarial networks. These people don't exist, but they look real, right? They have been created by morphing images. Okay, so this is what I'm showing you here in this case of generative adversarial networks. So it did run, and it's throwing an error here, so we have to fix that. We restart runtime and then run it. Okay, it's restarting, and we should be able to run this. Okay, so Basically, this particular body of knowledge is quite important for current trends in adversarial attacks and other areas that are out there. So you're most welcome to explore this generative adversarial networks. And this is a generator. It's creating a generator. And you see now you have a generator running, and it's going to generate noise here, and then discriminator, and it's going to create discrimination. Okay, and define loss and optimizer, discriminator loss, and then generator loss. And you save the checkpoints, training the loop. Then doing the training, then you generate and save images. Then you train the model. So now you see that, now see what is going on here. It's a training data set, different epochs. It's going to take some time to train this. And then you restore the checkpoint, and then you create the GIF, and it will show up. Okay. So you see now it's training first epoch, then it will run second epoch. There are 50 epochs is going to run, and it will see that the image will be generated. Now it's the second epoch, and the third, and the fourth, and the fifth, and you'll see the image being generated at that point. Okay. You see slowly it's being formed as the number of epochs are increasing. Now the numbers are generated. So you see that as it's going, you're not going to wait until 50 epochs are run, but you kind of get an idea on what is the generative adversarial networks. You create a generator, you create a discriminator, and now you are creating content by competing against each other, right? That's the fundamental knowledge. There are other areas where you are doing a lot of these type of generative adversarial networks and transformers. So you see see this different pattern style GANs, Google's Deep Dream, and Big GAN, different type of generative adversarial network, different style of watches can be created. You can describe an image, and it will create different type of values. These don't really exist. It's created by the computer. You have different type of dogs or different type of launch. You can show as if there's an explosion of the aircraft before it launches. You just fabricating everything. Here you're showing different type of dogs as they are being formed. Style transfer of Van Gogh on the images. If you remember, there was a Face app on iPhone. That was also through this generative adversarial networks. Art, right? Different type of art can be created, or style can transfer all these different styles. These people don't exist. It's been created by the style GAN. So all of this is interesting stuff in computer vision. that you can create experiences all the time. Okay, so now you see the 22 epochs. The other topic is around, in general, about Pytorch. So Pytorch is another library that's available from Facebook, which is similar to TensorFlow, but it is statically typed, so functional programming language. So it is compiled line by line, and it's much more powerful. Pytorch has been making much more progress in the industry right now in computer vision, because it's from Facebook, and Facebook has all our photos to Instagram and WhatsApp and Facebook. So they had a lot of data to train on, and that's why their computer vision models are much better than Google's. But it looks the same way it's getting trained. It has the filters, it has the same type of architecture. Just the way you write Pytorch is different, and they have much more automated functions that you can use for computer vision and for convolution network and so on. So we will also cover Pytorch in this class because Pytorch is equally important. Okay, so thank you, Angel, for your good words. Yeah, so you can just add me to your LinkedIn. You can just look for Vero Meta at Microsoft. You'll find me there, right? So essentially, this is what the course is all about. We're going to run it for 8 weeks, and we will cover all these topics in detail. The material I showed you is more for introduction. We have much more formal set of slides, and we go in a very curated order, so you don't have to worry about we are jumping around different topics today. It's just introductory class, right? The Pytorch libraries and they have a lot of these different libraries, also similar to the TensorFlow. So we can look at that also. So I just wanted to continue to show more items here. In this case, we are looking at the Pytorch segmentation routines and how it can be used for different object detection. Microsoft also has a Coco library that can be used for object detection. In this case, we are doing object tracking using Pytorch, right? And then same thing can be applied to videos. We can process videos and audio files, video files, and so on. So yeah, so if you have any questions, I can answer it, or we are out of time now. So please let me know if you have any questions.
Professor Mehta, so
yes.
Can you also give us a list of the link of these notebooks you have demoed today?
Yes, I will send it to you. Yeah.
Okay, thank you so much.
No problem. Thank you.
Professor, I have a question. Happy New Year.
Happy New Year.
Earlier you mentioned about this increase the neuron, right? And you also showed 28 different type of methods to reduce the overfit. Now, when you say increase number of neuron, is just increase the hidden layer or just add the neuron for the
Yeah,
existing.
it depends, you know. I mean, ideally, what people do right now these days is they just go over these type of networks. You see different all these different networks like ResNet, VGG, Inception. They just use pre-trained network nowadays. They don't design their own network. They tweak. They first start with this already developed network, and then they tweak it a little bit. These networks are usually very well designed, so you don't have to worry about training your own, because training is very expensive to do. But yes, you can add neurons, you can add dropouts, you can add momentum, you can change the learning rate, you can have dropout in visible layer, you can have dropout in invisible layer. So you can keep going in that direction. Yeah.
Okay, thank you.
Yeah. So any more questions? We still have 3 more minutes. Okay. If there are no more questions, thank you for your time. Thank you, Professor Quinn, for the opportunity. And we will keep going. I'll see you guys next weekend.
Thank you, Professor.
Thank you.
Thank you.
Are you still here, Bharat?
Yeah, I'm here.
Oh, hi.
Hey.
I'm Alice. I don't have a good background in terms of, let's say, advanced machine learning or deep learning. Do you have any recommendation of maybe online classes I could take to go along your class so that I could like maybe follow a little bit deeper what you're...
Yeah, I don't think you should worry about it. Most of my students don't have any background.
Yeah.
And that's how I teach. I start from 0 and go from there. So
yeah.
If there is a need, you can tell me after first or second session.
Yeah, I guess, I mean, it's not necessarily a need, it's for me to like understand.
Yeah, I can send you some materials. So if you drop me an email or a LinkedIn message, I can forward you great textbooks that Dr. Quinn has given me.
Okay.
I will send you those books and you can start with that.
You probably have a good understanding of like good classes and things you don't really necessarily recommend.
Definitely, I will share that with you too.
Okay.
All
right.
Sorry, Professor Angels, can you please send me the same textbooks to me as well?
Definitely, I will do that. Yes.
Thank you. We'll have a wonderful evening. Thank you so much.
You too. All right, guys. Thank you, everyone.
Thank you very much. Bye.
Thank you.